Hello? 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 Our session. Welcome to this online session. Welcome to this online session. Welcome to this online session. Actually, I'm muted. Actually, I'm muted. Okay, is that okay now? Okay, is that okay now? Okay, is that okay now? Okay, now let's double check. So now probably okay. Sorry, I found I opened up two different YouTube channels, so makes the echo. Sorry about that. So now let's start our session. So welcome all to this online session. This is a paper number 14. We have 4 papers about network sets. So for this session, we're gonna play all the pre-recorded video for all the presentation. And our paper also gonna be online and answer questions. So if you have any question, you can enter your question in the YouTube chat. So we will collect the question and make the Q&A after each video. So now let's start our first paper. The first paper is about metro maps on octilinear grid graphs. The paper is authored by Hannah Buster, Patrick Brossey, and Sabine Strong. So Patrick can present this paper.
Okay, hello everyone. Thank you for giving us the opportunity to present our work here today. So the topic is metro maps on octilinear grid graphs. Let's just dive right in with an example. This is the official London Tube map, which goes back to a map Harry Beck designed in the 1930s. This was actually one of the first public transit maps in this style, and since then such so-called octilinear maps have become the de facto standard. Octilinearity here of course means that each line in the map is drawn as an alternating sequence of horizontal, vertical or diagonal elements. The goal of our work now is to produce such maps automatically given the geographical network graph, we call it the line graph, as an input. So for example, given this input graph G of the Freiburg tram network, we want to produce such an octilinear drawing automatically and fast. Note that I said octilinear drawing, not octilinear embedding, which actually makes an important difference here, because we want to allow an arbitrary, but of course optimal, number of edge bands. So in an octilinear embedding, each edge is a straight line, and in an octilinear drawing, each edge is allowed to make as many bands as it wants, for example to circumvent this lake obstacle here, or to approximate geographical courses like the green line does here. Bands between station nodes are actually really common in real-world transit maps. They were present in a London tube map I just showed you, for example here and here. And they are used in this map of the rail network in southwestern Germany to approximate geographical courses between stations, for example here. So the high practical relevance of metro maps in general has led to numerous approaches to render them automatically. These are just a few prominent examples. In 2004, Stott used local search or hill climbing techniques to find octilinear maps. Then a year later, Nöllenburg and Wolf reformulated the problem, showed that it is in p-hard, and gave a linear program to render maps which actually look quite nice. Then in 2011, Wang and Chi described an approach based on a least squares optimization, which was, I think, further optimized 5 years later in 2016. One of the biggest problems of the approach by Stott was that the maps did not guarantee octilinearity, which in practice is a huge drawback because it is immediately noticeable by humans. Common to all these approaches is that they produce octilinear embeddings, so line bands along edges are not possible. This may be mitigated by introducing special dummy band nodes. However, you then have to know the number of bands you need beforehand, and if you enforce a minimum segment length, it may also elongate your lines. But by far the biggest problem of many approaches is that they simply take too long to be practical. So now the basic idea of our approach is to formulate the problem as a set of shortest path problems. Okay, shortest paths, but on what? Well, we built an octilinear grid graph in which edge bands along paths are explicitly penalized. So here on the left, you have a classic grid with diagonal edges and a uniform grid cost, and if you now calculate the shortest path from this node S to this node T, the resulting path may look like this and have many unnecessary bands. On our grid graph, edge bands in shortest paths are penalized, and the resulting path will look like this with the minimum number of bands. I will describe to you in a minute how this is done. So given such a grid graph, we now do the following. For each input edge, E going from S to T, we define a set of start node candidates, big S, depicted here blue, and a set of target node candidates, big T, depicted here red. And now the octilinear representation of this input edge E is just the shortest path from the set big S to this set big T here. Here on the right example, one of the input nodes was already settled, so the set of source node candidates here has a size of exactly 1. And after that path was found, it now acts as an obstacle for all subsequent paths, just like the red path up here acted as an obstacle for the blue path. And of course, a central question now is this: do we want to find all the shortest paths at once or globally? Or do we want to search for them iteratively or greedily? Well, we actually did both. We formulated a linear program to find them simultaneously, which produces globally optimal results, but we also experimented with the approximate iterative solution. Before we look at the iterative solution, let me just describe to you how the edge band penalties are actually modeled in our special grid graph. So here on the left, we have a small grid graph, and next to it we enlarged a single grid node. Our trick is now to add explicit port nodes, depicted here green, to each grid node, and explicit band edges, depicted here blue, between them. So to pass through a grid node, the path now has to arrive at a port node, for example at this one right here, take the corresponding band edge, and leave at another port node. The band edge cost is then set to reflect the cost for the actual band. So in this case here, it would be set to the cost of a 135-degree band. To actually arrive and not pass through at a grid node, we use explicit sink edges, which are depicted here in orange. The error cost now actually reflects the move penalty. Grid node candidates which are far away from the input node will get a high sink edge cost here, simply to make it more expensive to choose them. So with that in mind, let us now look how to find an octilinear drawing with the iterative approach. Well, we start with the input line graph. This is Freiburg again, and first contract all the degree 2 nodes. This is actually an optional step which is widely employed also in other work. It mainly speeds up the overall computation time and produces better looking results. And after that, we build a grid graph with the extent of the bounding box of the input graph. So the grid cell size here is a parameter of our approach, and we have found that setting it to between 75 and 125% of the average distance between nodes in the input graph is a reasonable choice here. And now we start routing the input edges. I won't go into details of how we choose the route ordering, but the general idea is that we choose the node with the highest number of adjacent lines first and work our way up from there. So we start at this central node here in the city center, and we just route its first adjacent edge. The highlighted nodes are the candidate nodes for the start and the end node of the edge, and their color depicts the move penalty assigned to them. So the greener, the better. This here is the path that is found. Now we settle this path as an obstacle, and we just continue and continue and continue, and slowly build up our octilinear drawing until we arrive here. So after we have arrived here, we now reinsert the contracted nodes equidistantly, and then it looks like this. And this result already looks good, but you can immediately see that there are cases where moving nodes a bit would lead to better results, for example, up here. And we are doing exactly that. After we found the initial drawing, we perform a local search where we move each input node to one of its 8 neighboring positions, reroute the adjacent edges, and check if the result is better than the currently best result. And if you do this, if you add this step, the final map will look like this. And you can just render it directly. So the question now is this: how much quality do you lose when you use this iterative approach compared to a globally optimal result? And we tested this. So here on the left, you have the final objective function values and solution times of a linear program optimizing this problem. And on the right, we have the corresponding values for our approximate approach. The last column here gives the approximation error delta added by our approximate approach. And as you can see, they're actually very close, but the approximate approach is much, much faster. For London, we could not actually find the optimal objective value with the linear program in under 24 hours, so we only know an upper bound of the error here. Okay, if you look at Stuttgart, this 4.1%, is this now actually bad or is this good? Well, let's look at the actual maps. On the left, we have the map rendered by the linear program, and here on the right, we have the same map rendered by the approximate approach. And as you can see, they look very similar, and only if you start searching, you find small differences, for example here, also down here. Well, a problem of our approach is actually visible here, and also here. Because we contracted these nodes here before octilinearization, this edge here is now not long enough to hold the reinserted nodes with an acceptable distance. For the approximate approach, we solved this by adding an additional penalty to the target function, which penalizes edges which became too short. Okay, let's look at a few results. All the results shown now are from our approximate approach with the station density penalty enabled. This, for example, is Vienna, octilinearized in roughly 200 milliseconds. This is the Berlin subway network, octilinearized by our approximate approach in around 800 milliseconds. This is Stuttgart again, this time with the station density penalty enabled. So this edge here is now actually longer. And this here is the London Tube map with rudimentary labeling enabled. So this labeling is actually done after the octilinearization and optimized separately. So this here is a comparison of our work to results from previous work using the Sydney light rail map. And as you can see, visually, our approach compares quite well to previous works. It is also faster than these two works, although we should note that the 150 milliseconds given here were not actually for this map, but for a map of similar size. This map was given without a solution time. Okay, so this here is a map of Freiburg, where our approach approximated the real geographical courses by penalizing grid edges too far away from the course. And as you can see, it can be used very nicely as an overlay over satellite images. And this here is Freiburg again, this time with a height penalty for diagonal edges, and we actually added a few obstacles here for lakes, park areas, and mountain ranges. Okay, so what else is there to do? As I've said, labeling is only implemented rudimentarily so far and optimized only after the octolinearization took place. We would like to experiment with base grids that have different node densities to further speed up our approach. And it would be very interesting to include node clustering techniques from previous work to the local search, simply to avoid falling into local optima. And something that looks actually quite promising is to test our approach on different base grids. Well, we're actually experimenting with it at the moment. This is work in progress. And here is a preliminary result of the Stuttgart light rail network rendered in an orthoradial fashion. So I think this looks actually quite nice. The base grid here, of course, was an orthoradial grid. Okay, thank you very much for your attention. If you're interested, our maps are available online here. Thank you and bye-bye.
Okay, thank you. Thanks for the video presentation. Now we have quite many questions. So the first question asked by Betty Speckman asked about which quality criteria using to capture the visual appearance and readability, especially for the comparison with linear programs.
Yes, thank you very much for the question. The criteria are actually mentioned in detail in the paper. So we're using the edge length, the number of edge bands, of course penalized by the acuteness of the band, and we use a move penalty. This is basically the distance between the station in the octolinearized maps and the original position of this distance. And these penalty values, they produce a final target value, which is optimized by both our approximate approach and by the linear program. So we can just compare them directly.
Okay. There's another question by Tim Grace. Have you compared your new map with the existing ones in cities, and are there noticeable differences?
No, we did not actually do that, but this would of course be extremely interesting. But I think it would be difficult to come up with the criteria to compare our maps to existing real-world maps, because they're made slightly different in the way they are drawn, and it would be very difficult, I think, to think of exact criteria to compare them. But it would be interesting nevertheless.
Okay, there are two more questions. So one quick one. The one question regarding focus on computational complexity. So you talk about in which application scenario having very fast algorithm for computing metro map could be useful.
Yes, so the main scenario we think of is, of course, a map editor. So if you have, in my opinion, it is quite unrealistic to expect that such maps are completely generated automatically in the future. So what you need are fast methods which help designers, for example, to design such maps and to give them suggestions, or to give them the opportunity to update the maps generated by our result, they have to give you a fast feedback, and for this you just need response times under 1 second, because otherwise the edit will be very painful.
Okay. The last question is asking about have you done some optional pre-processing in case of non-uniform scaling needed for this?
Yes, this is a very great question. Thank you for that. We are not doing any pre-processing at the moment, but we are actually experimenting at the moment with using different grids, which actually allow some kind of pre-processing or some kind of enlargement of different areas of the map. But at the moment, the approach presented to you in the paper does not do this.
Okay, so thank you very much. Thank you, Patrick. So now
thank you.
Go to the next paper. The second paper we're gonna present for this session is about augmenting node link diagram with topological attribute maps. It's gonna be presented by Reinhold Prinner. Can you switch to the video?
Welcome to this talk. My name is Reinhold Preiner. I'm with the Graz University of Technology, and I'm happy to present today our work on augmenting node link diagrams with topographic attribute maps. Imagine you have a dataset containing some entities, and these entities have logical relations to each other. So what you effectively have is a graph, and a typical representation for such a graph is a node link diagram that you see here. Now, if the entities contain additional scalar attributes, we talk about an attributed graph. And here these attributes are shown by coloring the nodes according to some color map. So let's say the nodes in this graph represent persons, and their connections, for example, represent family relations, like parent-child relations extracted from a genealogical database. Then a typical attribute to visualize would be the person's year of birth. Now, the analysis of such attributed graphs typically follows two main objectives that we need to take into account in a visualization. One is the analysis of its topological structure. In this example, an interesting feature might be the fact that this graph contains a topological circle. And typically we support the topological analysis by using a suitable layout for the graph. So the layout we see here might not provide the best possible comprehension of its structure, but other layouts like force-directed layouts, for example, can produce a node arrangement that much better reveals the structure and clearly shows such circles, here even without any edge intersections. Besides the topological aspect, we often also aim for an attribute-based analysis of the graph, for example to assess the overall attribute distribution or to perform relative attribute comparisons between nodes. Now, the problem is that in general the topologically structured layout shown here does not inherently favor an attribute-based assessment, because even when using color-coded nodes like here, it is still hard to mentally infer its overall temporal structure. To support this attribute-based analysis, we would therefore rather favor a layout that orders the nodes by their attributes, for example in a linear or in a radial layout. A usual approach for our graph here would be to arrange the nodes along a timeline and perhaps use additional grid lines to support the localization of the nodes on this timeline. Now, this layout makes it much easier to assess the temporal node distributions or perform relative age comparisons, but again diminishes the topological overview, as we have now in this small example already introduced an edge intersection again. So we see that in general an attribute-based layout conflicts with the aims of a topology-oriented layout, which becomes a problem when analysts need to combine these two objectives. In our work we aim to solve this conflict by combining a topology-preserving layout with an inferred contextual attribute landscape, which we illustrate as an underlying topographic map. We call such a map a topographic attribute map, or short a TAM. And in such a TAM, attribute values at nodes map to height values, which we interpolate to obtain a continuous height field. And by visualizing this height field using isocontour rendering, we can re-establish the relative comparability of node attributes that was before given by the grid lines in the linear timeline layout. For example, we can now again directly see the age difference between Joseph and Caroline, which is about 40 years, while we still preserve the topological structure of the graph. Now let's have a look on how we compute such a TAM. In the first step, we obviously need to define a layout for our node link diagram. That formally just means that we need to define an embedding that maps each node to a point in the 2D display domain. In the second step, we compute a height field that interpolates these attribute values at the node positions. In practice, we store this height field in a raster image of a certain resolution that encompasses the bounding box of the graph, and this height field is first initialized by rasterizing the node attribute values to this image. And then, based on these initial constraints, the remaining image is filled using a particular scattered data interpolation technique. In our work, we have investigated two state-of-the-art techniques, hierarchical diffusion and natural neighbor interpolation. Both are valid options. They both produce a smooth height field that interpolates the attributes at the nodes. They only differ in the exact shape of the landscape they produce. Then in the third step, the height field is rendered in the style of a topographic map. That means we map attribute values to a discretized or a banded color scale and show isocontours of the height field and apply Lambert shading to obtain a three-dimensional appearance. And finally, we also place height indicators onto the map. So here we start from some random seed locations on the map and then follow the integral curve of the gradient field and place a height label wherever this curve intersects an isocontour boundary. And in the last step, the node link graph is rendered on top of this map using node labels or other additional overlays that you might need for your graph. Additionally, we also allow for interactive highlighting of isocontours to foster explorative or comparative analysis tasks. Now, in the following I want to address two specific details on our algorithm that extend this basic computation pipeline. The first one addresses the visual embedding of the graph in the height field. So suppose we have this section of a node link diagram here that involves multiple smaller and a few larger backbone edges. Now, if we interpolate the height field based on the node constraints alone, then the resulting landscape does not quite reflect the topological structure of the graph, which is often dominated by the longer edges. In particular, if we follow these longer edges from a lower to a higher elevation, does not represent a monotonic ascent, but has to overcome hills and saddle points. So to improve the overall visual embedding, we therefore initialize the height field with additional constraints along the links that linearly interpolate their end node attributes. And this way, the edges become more naturally embedded into the landscape and follow a monotonic attribute slope. Now, while this produces a landscape that visually much better supports the structure of the graph, using edge constraints raises a problem when two links intersect at a point where both have different interpolated height values. Here we see two such cases in the detail region of this graph where edges at a lower altitude intersect with edges at a higher altitude. So here the question is which height value to use at the intersection point when we initialize the height field. One option is to just average these height values, which leads to smooth saddles that we see here, but now actually none of the edges exhibit a monotonic change in elevation. So instead we use a more natural representation that aligns with our landscape metaphor. If we interpret these edges as streets that cross at different altitudes, then we have two options to define the landscape at the intersection point. Either we model here a trench that embeds the lower situated edge and route the higher one over it using a bridge, or we raise the landscape to create an embankment for the higher situated edge and route the lower one under it using a tunnel. In our work, we chose the second option just because we found that tunnels have more distinctive symbols in topographic maps. So to realize this, we need to initialize the height field first with the maximum of all link height values at each pixel, and this creates such embankments when the height field is interpolated. And then when we render the graph overlay, we step along each of its edges and test the interpolated height value of the link against the height value of the attribute height field. This way we can distinguish between points on the edge that are above ground or underground. And we render such underground intervals using a common topographic style with dashes and tunnel glyphs to mark the entrance and exits. So this way we can achieve an improved visual representation of such link crossings. Now, to evaluate our visualization technique, we have applied it to graph data from different domains. In the first example, we have applied TAMs to a graph provided by researchers in edge computing. You see here a topology of 10 edge networks that are interconnected by an internet backbone node in the middle. And one of the goals is to reduce the overall data traffic by improving the resource allocation strategy. So ideally, computational tasks that operate on data should happen closer to where the data is stored in the network. Now this TAM here compares two different resource allocation approaches and shows the overall traffic volume they produce at each device node. So while on the left baseline method a lot of traffic is routed over the cloud in the middle, you can see that the optimized approach on the right heavily relieves the central backbone and concentrates the data movement at the edges of the network. Another use case, as initially shown, is visualizing large genealogical graphs. To this end, we have cooperated with two expert genealogists, and one of the datasets is shown here, comprising over 5,000 persons in about 1,700 families, and reaching back to the late 16th century. On the global scale, you can see the ancestral roots in the deep blue regions, or clusters of complex interrelationships that appeared here in around the 18th century, and also large circular connections that span 7 generations over a time range of over 200 years. So let's zoom into one of these regions to see the depth of this graph in more detail up to the individual families that we show here using red circles. Finally, I want to note that our method is applicable to other graph layouts as well. So here we see, for example, two TAMs of the family tree of Marie Antoinette, once using a forced layout and once as an H tree. And in the paper we also show how we can modify forced layouts to gradually obtain a more attribute-ordered layout. For this and for other extensions, as well as a report on a user study, please have a look into our paper. Thanks for watching.
Okay, thanks for the video presentation. Now we have a few questions online posted. One question asked by last lesson, asking about would it not make sense to allow for some relaxation for the node link diagram layout?
Yes, definitely. So you can alter the layout in general any way you want. We have focused in the paper on kind of finding a compromise between a classic rigid force link diagram, a force link node link diagram with a force layout, and introducing an additional force that tries to re-establish a bit the comparability between nodes of similar attributes. Besides that, depending on what your graph actually represents, or depending on the use case, any kind of additional relaxation or focus or other forces, whatever you want to modify in your diagram is possible. Also, of course, it's not necessarily, so we have here mostly seen or only seen linear edges. Of course, any kind of additional edge routing techniques or non-linear edge representations on top of that are possible. So,
okay, we have another question posted on YouTube. So asking about, did you find any other topographical or cartographic metaphor and glyphs that could be useful?
Well, so far, in the context of this work, we have not thought about, we have not used other typical topographic or cartographic glyphs. So the tunnel or the bridge glyph, this was basically the one thing that we resorted to visually resolve specifically these edge intersections. I could, though, imagine to introduce typical glyphs or typical symbols you use in landscapes or in topographic maps that indicate different vegetation states, like forests or urban regions or something like that. If you find it, or if you deem it useful to use this as an encoding of specific areas or regions or subclusters of your graph. So I can see, or I can think of, or I could imagine that a more heavily resorting on topographic known or well-known or established symbols could be indeed useful. So far, we have not investigated that, though.
Okay, so there's a message posted by Lars Linson. That's a follow-up message. He was asking about the relaxation to make the results look even nicer without destroying the topology. Okay, so yeah. Let's see. Probably we don't have any further question, but the results is very nice. So we see the first two tasks is all different maps. It's all one with those metro map we have very familiar with, and now we see this augmented map. It's quite nice. We hope we can see more of such map. So let's thank the presenter. Now let's move to the third paper. So the third paper is titled SAC Streams, Visual Exploration of Dynamic Overlapping Sets. This paper gonna be presented by Fabian Beck. So let's start.
Streams like these can show how elements change their grouping across time. On a timeline from left to right, you can follow individual elements. These elements, for example, might represent researchers working together on different topics. Over time, they shift their research focus and collaborators. While this representation is easy to understand and applicable in many scenarios, it comes with an inherent limitation. The limitation is, at each time step, the elements need to form a partition. But what if an element does not just belong to one group, but multiple groups? For instance, researchers might work on different topics simultaneously. This cannot be properly represented as a sequence of partitions. Instead, we need to visualize overlapping sets, which are dynamic. They change across time. Set visualization has already been discussed in various papers. However, surprisingly, there's only little research on visualizing dynamic sets. The recent state-of-the-art report describes it as one of the main open problems of set visualization. It is particularly challenging as time adds another dimension to an already challenging visualization problem. Nevertheless, few approaches have been published on the topic already, but none of them focuses on visualizing the evolving sets as streams that you can follow on a timeline. Our considerations for designing an approach like this were the following. We want to provide an overview across all temporal changes. For this, we need a timeline representation. Changes should be easy to follow. Streams provide a basis for this. In addition, we want to compare subgroups of elements and which temporal changes they undergo. The approach we suggest is called SAC Streams. To be able to represent the sets as streams, we first need to find a solution how we deal with the overlaps. The idea is to split the overlapping sets into exclusive intersections. These intersections are shown here as rows with combinations of colors, indicating which of the three original sets contribute to them. We do not consider all possible intersections, but only the non-empty ones. That is why the combination of purple and green is missing in this example. It is important to note that these intersections are exclusive, in the sense that an element can only be represented in one of them, namely the most specialized one. To give you an example, if an element belongs to all three sets, it will be part of the exclusive intersection of the three sets, but not part of any other exclusive intersection. These exclusive intersections are organized as rows and form the basis of the visualization layout of SAC Streams. The specific encoding, marked boxes representing the sets, is inspired from Upset, a tabular visualization approach for static sets. Now we can represent the changing sets as streams on a timeline. The time steps are arranged as columns from left to right. The elements, as they are only part of at most one exclusive intersection per time steps, can flow between the groups much like shown in the initial example. Elements that are new in one time step are represented as inflows from the top. Similarly, there are outflows of elements that are not considered in the following time steps at the bottom. Histograms at the top show how many elements are contained in the exclusive one-set intersections, two-set intersections, and three-set intersections. With this base layout, we already achieve our goals of getting a temporal overview and being able to follow changes across time. Still missing in the base layout is support for comparing groups of elements. For this, we introduce an interactive querying and selection mechanism. Two groups can be selected and compared. Orange and green color represents the groups. You can specify in a simple sentence-like format which set operation you want to use, on which participating sets, and based on which time step. This selection can now be shown as an overlay on the timeline representation. We use black color for those elements that are contained in both selection groups. As an alternative to using the query form, it is possible to simply click on a node or edge in the timeline. A respective query selection is then activated to select the contained elements. So this is the central timeline-based visualization of SAC Streams. But the full interface of our implemented solution, which you can see here, has some more views and features. To prioritize different base sets or characteristics, as well as to simplify the vertical layout, we provide various options for sorting and aggregating the rows. Moreover, there is a list of elements at the right side. To quickly find an element of interest, you can use the search field. Colored markers in the list reflect the current selection and can be used to inspect details. You can also click on one element, which then becomes highlighted as an overlay of the timeline representation in yellow. To demonstrate how to work with the approach and tool, I want to showcase an application example. It investigates how the expertise of researchers from a community evolves with respect to different subfields. We take the main authors of the visualization community as a sample. They form the elements. Now we want to learn how they shift their focus between the subfields of scientific visualization, information visualization, and visual analytics. The subfields hence represent the sets. We can extract this information from the publications at the IEEE BIS conference. We consider the time span from 1990 to 2015 and divide the publications by conference tracks: SciBIS, InfoBIS, and VAST. Please note that the original BIS conference is considered here as a predecessor of SciBIS. In SAC Streams, the data looks like this. The rows show authors that made contributions to only one track, to 2 tracks, or all 3. The columns show timestamps of a span of 3 years each. We have selected more than 1 year here to stabilize the movements. First, investigating the general structure, we clearly observe the origin of the conference series in the VIS/SciBIS track. The InfoVis track is branching in the mid-90s, and about 10 years later, the VAST track. The introduction of the VAST track was successful in the sense that the established researchers represented in this dataset also started publishing in this track right from the beginning. However, nobody immediately switched to only publishing at the VAST track, but instead new people came in that started with the VAST track only. From 2005, in general, the many diagonal connections between the nodes show good mobility between the tracks. Also, mainly in the last 2 time steps, all combinations of tracks are non-empty and populated by multiple authors. This shows that the tracks do not separate the community. In the period of 2005 to 2010, the situation was clearly not as balanced between the tracks yet, but still more focused on SciBIS/VIS. Second, we contrast particular groups of authors. For instance, we can compare the group of early contributors and the group of recent generalists. The groups only share one researcher, Jack van Wyk. Many of the early contributors are still active in the community, as only few orange edges leading out at the bottom. These authors have spread across all combinations of tracks. Further, it is interesting to note that the recent generalists all started their contributions to the conference with contributions to SciBIS/VIS. The green incoming edges all lead to the exclusive SciBIS/VIS node. You can find 2 more application examples in the paper. One on studying the evolution of the Linux project and its main contributors, and the other one on analyzing the training phase of a multi-labeling image classification algorithm. So this is our approach called SAC Streams. It visualizes dynamic changes in set structures, providing a temporal overview, supporting to follow changes across time, and to compare groups of elements. You can check out our tool online or find more details on the approach in our paper.
Okay, thanks for the presentation. Now we have a few questions asked. So the first question raised by Martin Nuremberg is called ask about scalability. So we see in the demo you showed there are a few only a few cells so intersect with each other. So the question is asking about what's the kind of a maximum number of different cells and their exclusive intersection. Does your visualization still work well?
Yeah, that's a good question, and we have a bit more larger examples in the paper, but actually it's definitely a limitation of the approach that with 6, maybe 7 base sets that heavily overlap, of course the number of non-empty intersections get larger and larger, so we need to add rows and rows. This is very similar to other set visualization approaches, like imagine an overlay-based approach where you mark different areas. It's also hard to read then the heavily overlapping regions. So we have the same problem here as well. So we haven't solved this completely. We have some ideas about that. Some relate to these aggregation approaches where you can blend out, for instance, intersections of many sets. There are more details on this in the paper and the discussion on this in the paper as well. So we have some ideas for future work here. We have implemented some features in that direction already, but yes, like with other set visualization, this is a scalability issue. And this is one of the, as far as I see in set visualization, for many approaches, one of the unsolved problems, how to scale the number of sets, especially if the sets are overlapping significantly.
Okay, thank you. So the second question asked by Silver about how do you handle different temporal granularity and temporal stability?
So we have chosen here quite large timestamps also to circumvent this problem of temporal stability. That all depends on the input data, and of course for like a publication data set, it doesn't make sense to use just yearly data because this is much too unstable. So it depends very much on the application at hand, and it's not really in the scope of this work to kind of suggest algorithms how to stabilize. We just consider this as input, but in some application areas that's of course an issue, and that can be done as a pre-processing step to stabilize the data. Otherwise you might misinterpret that people are switching between fields, but it's actually that they don't publish every year in every field they are working on, for instance. But it depends, the temporal granularity depends on the application, of course.
Okay, yeah, I see some questions streaming in now, but not show up fully yet. So it's like our streaming paper on set. Let's wait a little bit. I think someone is typing in the system. So where other person is typing, maybe we ask you a few things. So for this one, like enhance about this streaming sets. So how about like if you consider those sets, they have also other variables. So if we're like combine with other variables, what kind of thing you may thought about to solve a more complicated issue?
So like you have attributes to the set membership, for instance, right? We are working on an approach and have a tool ready. It's under submission where we have weights. This would make the whole thing more complicated. So here adding weights could be done if you scale the streams. But since we don't represent the individual elements and those weights might change over time, or the weight can also contribute to different sets in a different way, that is a bit tricky to integrate here. Of course, you can do stuff with details on demand, but that would not be maybe a full integration. So for full integration, we are actually working on this alternative approach that we will hopefully publish soon.
Okay, so now we have one more question. The other question is finally fully streamed in. So it's asking about the encoding. So the question indicate like I saw that the set size is encoded by the height. So for the smaller sets that lead to a couple of thin gray bars, have you considered other encoding that highlight difference between better for smaller sets?
I'm not sure. So we need one property, and that we share, I think, with the Sankey diagrams in general, which are the basis for this kind of layout, is that the weights of the elements add up. So of course we can manipulate the weights of individual elements, but if we would use a logarithmic scale for the streams, they won't add up anymore. So I'm not saying it's not doable here, but it might have other consequences, and I'm not sure those consequences would not affect the readability or the interpretability of the diagrams. Not sure 100% I answered the question.
Yeah, okay. So maybe we can discuss more offline. So we can put the question and answer in the Discord panels. Okay, thank you very much. Thank you, Fabian, for the question and the presentation. So let's move to the last paper for today. So the last paper is about quantitative comparison of timing-dependent tree maps. The paper going to be presented by Max Songdai. Yeah, let's go ahead.
Hello, I would like on behalf of my colleagues to present this work called Quantitative Comparison of Time-Dependent Tree Maps. Tree maps are one of the best known methods for visualizing hierarchical datasets. They stand out for being able to handle very large amounts of data. Given a weighted tree, tree maps recursively partition the 2D space into areas that represent the structure and weights of the input tree. Most tree maps use rectangle, although there are alternative models such as Voronoi, L-shaped, and jigsaw tree maps. But on this paper, we will focus exclusively on rectangular tree maps. There are many different rectangular tree maps algorithms in the literature, and different designs work around different constraints and focus on different aspects, such as visual quality, order preservation, readability, or stability. This last aspect will be the focus of this work, since we are interested in portraying time-dependent data. The contributions of this work are as follows. We introduce a new method to measure the stability of time-dependent tree maps, which explicitly considers the input data. This is important because previous metrics would only consider the amount of on-screen movement and disregard that this is the expected behavior when there is large data change. We propose a novel classification scheme for time-dependent datasets, as we notice that the characteristics and dynamics of the dataset plays a crucial role in the quality of the tree map. So we compute these features and test the techniques according to these classes. Lastly, we perform a quantitative evaluation of 14 rectangular tree mapping algorithms in more than 2,000 datasets. The 14 tested methods can be divided into 3 categories. Unordered tree maps that do not need to adhere to an input order, which typically helps the algorithm achieve good visual quality. Ordered tree maps, which are required to adhere to the order of nodes as given in the input, which in most cases ensure that rectangles close to each other in the input are close to each other on the result tree map. And state-aware tree maps, which may use the layout of the previous time step to compute the new layout, helping control their stability. We measured quality regarding 2 aspects. Visual quality, in which we are trying to maximize the aspect ratios of cells. We measure this because it is easier to estimate the areas of squarish cells than elongated ones, thus improving the readability of the visualization. Besides, this is the most popular measurement in the literature. And we also measure stability. Here we are trying to minimize the amount of movement in the layout, as excessive movement might negatively affect our comprehension of the data. But when the data changes a lot, it is inevitable and desirable for the visualization to change considerably. So, how do you measure the stability and not penalize high movement generated by large data change? Imagine that you have an initial input tree and corresponding tree map layout. On the next time step, there is some data change. Weights might change, and a new cell is added. This triggers a visual change. But how can we tell if this visual change was proportional to the data change? Especially since these 2 amounts are not directly comparable. What we can do is to estimate the minimum amount of movement that may be generated by a given initial layout and data change. This new baseline layout is directly comparable to the actual visual change, and given that, we can estimate how much unnecessary movement was created. The third element of our evaluation are the datasets. For this project, we've gathered over 2,000 time-dependent datasets from different sources, such as GitHub repositories, World Bank indicators, movie reviews, sports data, among others. On previous works, we notice that the performance of tree mapping algorithms depends considerably on the characteristics and dynamics of the data. Therefore, instead of simply gathering a large number of datasets, testing and aggregating the results, it makes sense to classify datasets into classes and understand how these affect quality. We've chosen 4 features: number of levels in the hierarchy, variance of node weights, weight change, and number of insertions and deletions. Obviously, other features can be used to characterize the trees. However, for practical reasons, we must keep this number low. We hence limit the analysis to these 4 features. Each feature is subdivided into meaningful ranges, generating 54 combinations which can be analyzed independently. The graph on the right shows the number of datasets that fall within each class. For example, we have 114 datasets with flat hierarchy, low number of insertions and deletions, high weight variance, and regular weight change. As you can see, even with just 4 features, we couldn't cover all the classes. To validate our classification, we analyze the consistency of results within a class, for classes with 50 or more datasets. As we can see on the table, nearly all data classes for visual quality and most data classes for stability get more consistent quality results than compared to a random sample. This indicates that our features are indeed splitting the datasets into valid data classes, where the relative performance of an algorithm is easier to predict than the random baseline, adding strength to our choice of analyzing methods relatively, depending on the characteristics and dynamics of the datasets. Running all algorithms on all datasets and measuring the quality of the output with the 2 types of metrics, we arrived at this very aggregate result. Here we have a plot for each of our 4 features. The performance of each algorithm is presented by a polyline, in which the points of the polyline describe the different ranges of a feature. The x-axis shows visual quality, that is, a measurement closer to 1 means that the cells in the layout resemble more squares than elongated strips. And on the y-axis we have stability, where a value closer to 0 means stable layouts. The color of the polylines is given by the class of the algorithm. Another 2 maps are blue, state-aware are purple, and the remaining ones are the order techniques. For presentation purposes, we will focus on only one of these 4 plots, though we can see some resemblance between the 4 of them. Let's focus the analysis based on the number of levels in the hierarchy. A trend we see here and on the other plots is that other techniques, such as square foot and approximation, score highly on visual quality. Notice also that their visual quality decreases with the increase of the number of levels in the hierarchy, whereas slice and dice consistently gets poor visual quality results. But here, the visual quality increases with the increase of the number of levels in the hierarchy. The remaining techniques score somewhere in the middle. Let's now look through the stability lens. On all 4 plots, slice and dice and the state-aware techniques score highly stable results. All other techniques show instability at different degrees. But it is important to notice that state-aware techniques, that is, local moves and grid insertion tree maps, on top of being very stable, get good results regarding visual quality. Also, the results vary less with regards to input characteristics, making them more consistent. But as you can see, there is no algorithm that performs best on both types of measurements and on all data classes. Hence, the answer to which algorithm to use depends on the desired trade-off and the data class in question. The results we just shown are heavily aggregated. For finer grain analysis, you may check out the paper or our online repository that contains all of our results and raw data. Here you may also find all the datasets we use for download, along with the algorithm implementations. To conclude, in this work we performed an extensive quantitative evaluation of tree mapping algorithms for time-dependent data. We introduced a new method to measure stability, which explicitly considers the input data. And we proposed novel classification scheme for time-dependent tree datasets. All of our data, metrics, and algorithms are publicly available and can be found in our repository. Thank you for your attention.
Okay, thank you for the presentation. That's a very comprehensive use study. Yeah, for this comprehensive study for those different temporal varying tree maps. So actually, I haven't seen people post a question. So yeah, let's let me ask some simple question, and let's wait if other people wanna post more. Okay, so like based on your observation, so when you compare those ones, so what's your you see compare with those ones? So what's the most major conclusion from your quantitative study for those different time-dependent tree maps? Another one is actually we saw a lot of tree map. Actually, for each tree map, when there's a different constraint. So the one constraint is we want to keep this hierarchical structure, where for different data sets, actually the behavior could be very different. So have you also considered for those algorithms, when we study their behavior, consider how the data actually maybe challenge or change their behavior metrics?
So we classified the data according to these different features, because indeed, if the data changes, then your tree maps behave differently. So if you have more levels of hierarchy, some algorithms work better, and mostly for the non-state aware. So the more levels of hierarchy you have, the more stable they get, as there are less changes in this thing. So the type of data that you're having really influences the results for all of these things.
Okay, I see. So yeah, actually, I haven't seen other question posted. So probably if someone want to ask more question, all the authors are available through email, and you can contact them through email. Okay, so now we'll finish our full video presentation for today. So we have a very good presentation today, and we see a different aspect for this network sets. We see a lot of beautiful map. We have those dynamic thing, and we also have a good comparative results. So let's thank all our authors, and thank you very much for your presentation and all the Q&A sessions. And we also would like to thank all the people who are watching the video. And so this is a very unique experience. We share our paper online. So thank you very much. And let's conclude our session. So thank you again. Bye-bye.